In sac110 problem number 4, the person throws a rock. Let's draw a little bit of a rock here. They launch it with a launch angle of 39 degrees above the horizontal. Call that theta. And over flat level ground from a height of 0.668 meters. So let's draw some flat level horizontal ground and indicate that the rock is up there at, I'll call that Y0, 0.668 meters. So this is my reference level. In fact, I'm going to use a coordinate system that looks like this. I'll call this the x-axis. Upward, no, the y-axis. I'll go with y on that one. And this blue line represents the x-axis with positive to the right. So it starts out at x is equal to 0 and y is equal to y0 of 0.668 meters. Alright, let's see. It goes downrange a distance 7.4 meters. So indicate a trajectory for this rock and label this distance. I'm going to call that the final x values. I'm also going to use a symbol x for that. And that's 7.40 meters given right here. It bounces around. They want the momentum of the rock at the instant it leaves the thrower's hand. Well, that's just going to be the initial velocity times the mass of the rock, which is given. And the direction will be, we're given everything about the initial velocity, so downrange at an elevation of, or at an angle of 39 degrees above the horizontal. So all we have to do is find the value. I say we're given everything about the direction of it, actually. We're only given everything about the direction. And what we need to find is the magnitude of that initial velocity based on how far it goes. So let's have a look at some constant acceleration equations, because that's what we got here. We got a constant acceleration of a sub g, positive value of a sub g in the downward direction. So I'm going to take a look at the y motion. It lands on the ground, so that tends to govern the time. Y is equal to y0 plus v0y times t plus 1/2 a sub y t squared. Okay. v0y, see, one of the first things I gotta do is to break up v0 into its components. So I'll draw a little vector component diagram for v0. It'll be the vx direction, vy direction for this abstract diagram. We call them directions, but positive values increasing in that direction on the diagram. So put down a v0 vector and the theta, which we do know is 39.0 degrees. Keep myself reminded that that's a known quantity. And v0x and v0y right there. v0x from that diagram I can tell is given by v0 times the cosine of theta based on the triangle. It's equal to the hypotenuse times the cosine of the angle. And here I'm looking at the opposite, which is equal to the hypotenuse times the sine of the angle. So I've done my vector component diagram, broke it up into components, and found expressions for each one. And this is the one that I need right now, the expression for v0y. So I'm going to substitute that in there. Let's see, can I cross anything out? Yeah. We're looking for the special time t at which the elevation becomes 0. So this t, since I'm making this 0, represents the time at which the object lands. Alright, so I'll have 0 equals y0, that's what I call it right here on the diagram, plus v0y, we just found it as v0 sine theta, times t, and then plus the 1/2 a sub y. That's how fast is it moving in the upward? Well, what's the acceleration in the plus y direction? And that's a minus ag. So the component of the acceleration in the y direction is minus ag. I can multiply that by t squared. And I've got an expression involving the time and the unknown initial velocity. And the time is unknown, so I'm not going to be able to solve for anything there. Let's work on the x motion. So this was y motion. I should title it. X motion. We have no acceleration in the x direction, so the x position is just going to be the initial position plus the velocity in the x direction times the time. You can add on plus 1/2 a sub x t squared if you want, and then cross it out. But for the x motion, we know we have no acceleration, so I'm going to start without it. And I chose a coordinate system for which x0 is 0. So the initial position of this object is x0, y0, which is equal to 0, 0.668 meters. So this is a 0, and this makes this relatively simple. X is just equal to, now do the pure substitution, v0 cosine of theta times t. And that's got the same two unknowns, the t and the v0, which the v0 is what I'm looking for. So what I'm going to do, I'll solve for the variable that I don't care about, I'm not looking for, in one equation, and then substitute that into the other equation. It goes there and there. And then I'll have one equation and one unknown, namely v0, which is what I'm looking for. So I'll be in pretty good shape. I'll almost be done here. So you got y0 plus v0 sine of theta. Then pure substitution. I'm not going to do any simplification here. Just write in what I'm substituting. For t, it's v0 times the cosine of theta. And then plus the 1/2 minus a sub g times t squared, which will be x over v0 cosine of theta. All squared. Okay, now I'll simplify a little bit. I do want to solve for v0 eventually. Looks like it cancels out right here. And I'll write this as 0. I'm going to move down a little bit. 0 is equal to y0, initial y position, initial height. Alright, sine of theta over the cosine of theta is the tangent of theta. It's not important that you make that that you recognize that in that replacement, but I choose to here. So that'll be x tangent of theta, and then I'm going to take this minus sign outside the expression, And I've got x squared over VO squared cosine of theta squared. I'm going to put the AG up there in the numerator. So I've got A sub g times x squared upstairs. And I'll put the 2 in the denominator. Remember, all this stuff is getting squared. I think I'll go 2 cosine of theta, so I'm changing the order a little bit, times VO squared. Alright, I got to solve for VO squared. I'm going to add this term to both sides to get VO squared on the left. Write it slightly differently, so I've separated the 1 over VO squared part, and that's y0 plus x tan theta. Now I'm going to multiply both sides by 2 cosine theta over agx squared. So I'll just have 1 over VO squared on the left, and then a big mess on the right. 2 cosine of theta. Seems like that was squared up here. This was squared right there. So I got the x squared, I got the cosine of theta squared, and I got the VO squared. Let's fix that up. That's squared. So now multiplying by 2 cosine of theta squared over, I'm multiplying this side by that, so I'll go ahead and write down what I had on this side. YO plus x tan theta. And then that's all being divided by, multiplying both sides by this over that, so I got AGX squared. Then I'll take the reciprocal of both sides and take the square root of both sides. So I'll get, I guess the square root reciprocal of x over cosine of theta out here times square root of 2 y0 plus x tan theta all over a sub g. Is that right? No. Oh, under a sub g because I'm taking the reciprocal. There we go. Took the reciprocal and the square root of both sides. Reciprocal of this piece, square root, is x over cosine theta, and the square root of the reciprocal of the 2 times this divided by that is this piece, divided by the 2 times the quantity in parentheses. So I think I'm ready to evaluate this expression. Let's go. VO is the x, total distance traveled, was 7.40 meters. Divided by the cosine of the angle. I think that was 39.0 degrees. Let's check though. 39 degrees. And I'm going to need YO is 0.668. Plus our 7.40 meters times the tangent of that angle. And I'll make that a square bracket. Extend the square root all the way over. And go ahead and evaluate that on the calculator. And I get VO is equal to 8.167 7. I'm keeping too many sig figs. I'll call that a 3 is the next digit rounded. Meters per second. And the thing was, all that work to find that, but they wanted the momentum of the rock the instant it leaves the thrower's hand. And the rock has a mass of 1.10 kilograms. Okay, so what I'll go is find the magnitude of that momentum. Call that the initial momentum magnitude. That's going to be MVO, which is just the 1.10 kilograms I just looked at, times the 8.1673 meters per second. Plug that into the calculator, and I get PO in magnitude is 8.98 kilograms meters per second. The PO vector itself with magnitude and direction is 8.98 kilogram meters per second with a direction of I'll go in the forward or downrange direction. So as far as the compass direction, they didn't give us one, so I'll just say forward at the given angle of 39.0 degrees for the initial velocity above the horizontal. That's my answer. Let's do a couple of quick checks. The units, kilogram meters per second, that worked out there. I should check the units here. Oh my goodness, I left out units. That makes it hard to check them. But that was Y0, which has units of meters. So I can fix that up. So I got meters divided into meters per second squared. So that's 1 over second squared. Take the square root, I got 1 over seconds, and then multiply that by meters, I got meters per second, which is what I assumed it was going to be. But now I've proved it to myself. So it did work out to be to have units of meters per second. And does that just makes sense? They throw it at 8 meters per second. That's pretty fast, and it goes 7.4 meters. It seems reasonable to me. So I'm going to stick with that. I go try to write that 8 a little bit more clearly for you, and then call that my final answer for SAC 1.